Hello guys, welcome to my YouTube channel. I'm Naftal. In today's lecture, we want to talk about quantum mechanics. And in quantum mechanics, we want to talk about a particle in one-dimensional box. This is what we call sometimes the infinite potential well. Now, in order to study this, we want to consider a particle subjected to a potential energy function such that the infinity is everywhere along the axis of the box that we are going to draw here. This is what I'm talking about. Now, this is what I'm saying. It is infinity. This is to infinity. We consider this is x is equals to, these are the dimensions of our box. Now we consider a particle in here, and the potential of such a particle is equal to 0, but those outside the box is equal to infinity. Remember we said, and we consider a particle subjected to potential energy function and that it is infinite everywhere along the x-axis except for the box where our particle is. And also this means this is equal to infinity, and therefore we can say this is region 1, this is region 2, and this is region 3. Now remember, in the previous lecture we talked about the time independent Schrodinger wave equation. Time independent Schrodinger wave equation, and we decide that is equal to negative h cross squared over 2m, the second derivative of the wave function, plus the potential times the wave function will be equal to the energy of such a wave. Now we start with region 1. So in region 1 we decide our potential is equal to infinity. Now we'll take this infinity, we put here, because from the wave we want to derive the equation, the probability, or what is the wave equation for such a particle in this box. That's what we want to do right now. And we say negative h cross squared over 2m, the second derivative of the wave function, plus infinity, the wave function, will be equal to the energy and the wave function. Now we take this term to the other side. Now negative h cross squared over 2m, the second derivative for the wave function, will be equal to energy minus the infinity times the wave function. This is a very large number subtracting from a very small number. We can neglect e, because this is a very large number subtracting from a very small number. We can neglect it, and because the value we are going to get will be negative, that value, so we'll maintain our negative. So negative h cross square 2m, the second derivative of the wave function, over will be equal to negative infinity, our wave function. Now negative and negative will cancel. We remain with h cross square 2m now I want to make our wave function the subject of the formula. It's like we will say this is times 1 over infinity times 1 over infinity, such that infinity cancels here, and we say the wave function will be equal to 1 over, this is infinity, infinity times h cross squared over 2m, the second derivative for the wave function, and this is a very large number divided by a very small number. It's like we take 0 divided by a number, it will be 0. Therefore, this means that the wave function in region 1 is 0. Now, we want to derive for region and again we derive the equation for the region. We come to region 2 later. Let's derive for region 3. For region 3, where the potential is equal to infinity, it will follow the same procedure, and therefore if you insert infinity, we'll see that region 1 and region 3 have some similarities because the potential here is infinity. Therefore, this wave equation will be also equal to 0. Therefore, it means there is no probability of finding the particle outside the box. Now let's consider region 2. So in region 2, we said our potential is equal to 0. Now from the Schrödinger time independent wave equation, we'll say negative h cross squared 2m, the second derivative for the wave function, over x squared, now plus this is 0. So if you insert the potential here to be 0, it means this whole part will become 0. So plus 0 will be equal to the energy times the wave function. This means that a negative h cross squared over 2m, the second derivative of energy, will be equal to this one. Now we want to find to make the second derivative to be the subject of the formula. So the second derivative here will be equal to, I'll multiply, I want to take this part to the other side, so it's like I multiply with 2m over negative h cross squared times 2m over negative h cross squared. So I'll get 2 will be equal to 2m e over, this is 2m e over h cross squared, this is negative the wave function. Now this is an ordinary differential equation which is has a standard form. In the form we'll say, okay, before we left that standard form, let's say this part to be equal to k squared. So where k is equal to 2m h over this one, then the root, isn't it? We say that part to be equal to, we say this part to be equal to k squared. So this means that the second derivative of our wave function will be equal to k squared, the wave function. Now we can say this has an ordinary differential equation solution which goes in the form cos kx plus b sine kx. Now, and where a and b are constants. Now if we take this is therefore the time independent Schrödinger wave equation for finding the particle in region 2. Now here we say if our psi of x is equal to 0, therefore x is equal to 0. So if we say this is 0, therefore it will mean a cos k times 0 plus b sine k times 0, which means this is 0 will be equal to a. This means the whole of this part is 0, therefore cos 0 is 1 plus b times 0. This means a will be equal to 0. So if we say a is equal to 0, if we insert 0 here, the whole of this part will cancel out, and we say the wave equation will be equal to b sine kx. Now, this is what we can say that is the equation for finding the particle at the